what do we notice here about the output? How many outputs? Yeah. So this is the input x, y are the inputs to the network, and you have the output, which is a single output, right? However, if you notice now, we want two outputs. We want to control theta 1 and we want to control theta 2, right? So what does that mean? How many ANFIS networks do we need to control a robotic arm with two joints? Two, right? That means you're going to create and build two separate ANFIS networks. One for theta 1 and one for theta 2. One will use the training data of theta 1 xy, and one will use the training data of theta 2 and x and y. Here, so that is one thing you need. This is in contrast to multi-layer perceptron networks, which you can put as many outputs as you wish. So that is the one thing, or the first thing you need to pay attention to. Now, moving on from that, let us look at the actual pre-existing MATLAB code. So the good thing is you have a pre-existing MATLAB code for two ANFIS networks that have two joints, for a two-armed robotic arm with two joints. You'll use this as your base. You'll build on it. So you'll use it to test and manipulate all the different parameters until you get the best performance. That's the first thing. You will build on it to extend it to a three-arm robotic arms, so three joints. And you will also look into what can you use from it when you're building your two arms MLP, multi-layer perceptron, and your three arms MLP, which I'll show you in a bit. So this here is a pre-existing code. You'll find it here in your ANFIS class practical called inverse in-kind code path, inverse kinematics. By the way, inverse kinematics means that, so now we use the forward process. We use the values of L1, L2, theta 1, and theta 2 to find x and y, right? So we call that forward kinematics. The inverse kinematics is when your input is x and y, and your output is theta 1 and theta 2. So your code here, or your neural network here, is actually doing the inverse process. It's an inverse kinematics, okay? So here, you'll have plenty of explanation of what is inverse kinematics, why are we using fuzzy logic for it. So if you go through this, and this is part of your task, is to go through this process, I will just jump into the code parts of it. So here, in the example, you have pre-existing values for L1, L2, and for theta 1 and theta 2. Yes? So for example, theta 1 is from 0 to pi over 2 with a step of 0.1. So it means the generated values for theta 1 are equal to 0.1 degrees, or sorry, 0.1 radians, 0.2, 0.3, 0.4, all the way to pi over 2. Yeah? And here we have from 0 to pi with again a step of 0.1. So the step tells you how many data points we're going to have, right? Because for every combination of theta, or for every point of theta 1, you're going to have a value for x and a value for y, right? So therefore, the number of steps can tell you how many data points. So if I change this, for example, instead of 0.1 to 10, does that mean I'll have more or less training data points? Yes, right? Because instead of having, for example, just between 0 degrees and 20 degrees, with a step of 10, you'll have 3 points, 0, 10, 20, right? But with a step of 0.1, you're going to have 10 times that number, right? So this is the first thing you need to consider when you're trying to manipulate different parameters. The number of data, the spacing of these data points, and so on. So here you'll see that first thing you do is you create two columns, theta 1 and theta 2, which are the values that you decided in this line here. Okay? Then we're going to calculate the values of x and y using the formulas that I just explained to you. X is equal to L1 cosine theta 1 plus L2 cosine theta 2 plus theta 1. And y is equal to so and so. So these two lines are the formulas that I just explained to you using Pythagorean theory. Then here we're going to create two data sets. One for theta 1, which we're going to use with the ANFIS network that will predict theta 1 value, and one for theta 2, so I can use it with the other network that will predict theta 2 value. So the first data set, and remember, data set has inputs and outputs, right? So here we have the inputs will be x and y, and the output will be theta 1. And the second data set will be input is x and y, but the output is theta 2. Okay? So here we did the forward kinematics calculation. And here we're going to use them for the inverse kinematics neural network. Okay? Up to this point, are we all clear? Yes? No? Good. Then, further explanations. I'll leave all of this to you. It's very self-explanatory. Here, we're creating an ANFIS network. So these are all the parameters related to the network, the number of membership functions, the epochs, the number of cycles, and so on. Now, for MATLAB, whenever you have a question, you're not sure what a line does, what this function does exactly, you are advised to go straight to the lookup. Is it just a moment? Help here. And write the code line or the function that you're not sure with, and it will give you all the instruction about the function. Clear? So here we've done the design, we've done the basic information, how many membership functions or how many rules, how many training iterations are we using it, what is the minimum error that we're accepting, and so on. Then here you're going to train the network ANFS1, or build network number 1, using the data set 1 and the operations or the properties from here. Okay, and you're going to display the network performance, and then again we're going to do the exact same thing for a second one, and this time we're going to train on the second data set, the one with theta 2. So you have two artificial neural fuzzy systems, one for theta 1 with the data that we've predicted for theta 1, and for theta 2 with the data of theta 2. And then you're going to look at validation of the network. So for validation, now we talked about validation previously, and that, for example, for neural networks, we take the data that we have, we break it into 3 categories, right? Training, testing, and validation, right? So that is one thing. The other option of validation is that you compare to actual data. Here we're going to do the inverse kinematics mathematically. So I did the forward kinematics mathematically using Pythagorean theorem. If I want to do the inverse process where x and y are the input, here are the formulas. And I advise you to go look them up online. They're using matrices, they're using Jacobian. There are different approaches to find the same thing mathematically. So here, these are the mathematical formulas to find the values of theta 1 and theta 2 based on the values of x and y, where we have C2 and S2 as intermediate variables. Okay, just to explain the process. So what you're going to do is you're going to create data types or data sets, training data, build the network, then compare the network's analysis or validate the network using this validation equations, which are another mathematical. Okay? So therefore you get to compare the error of the first and the second network by comparing the network prediction to the network training data to the network validation formula. But this is a mathematical formula. And the network is predicting what this network is calculating. So you see the difference? This one is calculating while your network is predicting. Now with that, you can actually calculate the error rate, like the prediction, the calculation minus the prediction. That difference is the error rate. And then you can plot the error rate to see the network performance. So if we take a quick run of this, you'll see the error rate plotted. So up to this point, is it clear for you? So this is a pre-existing code. Yes?
Excuse me, doctor.
You take this for task 1. Task number 1 will be taking this code, not changing the code, but just changing the parameters in the code. For example, the error rate, the number of training cycles, the number of membership functions, or the number of training data. Do all of these tests and see which combination of change parameters give you the best performance. And when I say best performance, it means, remember, we start from random weights, right? So to ensure that this performance you're getting is the actual best performance, the rule of thumb is run the same design 10 times and get the average of these. Once you get that, then you're done with task number 1. And you go to task number 2, which is do the same thing, but use multi-layer perceptrons. Now, a hint is you don't have to regenerate or write the code for generating training data, because you already have the training data. You can use the same data to train multiple networks. To use the same data to train the multi-layer perceptron network, again, play with the parameters, the number of hidden layers, the number of neurons per hidden layer, the minimum acceptable error rate, the number of training iterations, and so on, until you get the best performance, and then that will be task 2. Task 3 will be to compare these two best performance networks in terms of performance. Task 4 will be to take this code. Now here the data is ready. So if you see, the plot here shows you the error rate. And it's within the range of 5 times 10 to the power of minus. So it's less than 0.005. Now, task 4 would be to take this same code, but add a few bit more lines and maybe edit some of the lines so that it will be for a 3-arm planner. So instead of this setup that we have, assume that you have another setup where we have 3 arms. So this is arm 1 with length L1. This is arm 2 with length L2. And this is arm 3 with length L3. So we have theta 1 and theta 2 and theta 3. Okay? So based on that, let's just make them a bit more realistic extensions. Theta 2, this would be L3, theta.
Excuse me, doctor.
So you'll do the same, you take the same code, but edit it, add a line. So obviously the math will change here for XY coordinates because you have to add that third extension. So figure out what is the new formula would be. The new mathematical formula for X and Y in ANFS network, because it will change. Previously it relied only in 2 thetas, now we have a third thing. Update the mathematical formula to create the training data. Create 3 different networks, one to predict theta 1, one to predict theta 2, one to predict theta 3. Manipulate the parameters in these networks to get the best performance. Create a new multi-layer perceptron network to predict again theta 1, theta 2, theta 3. Compare the 2 networks, ANFIS and multi-layer perceptron. And when I say compare, the comparison is in many factors. The size of the network, the computational overhead that it needs, how long it took to train it in terms of time, how long it took to train it in terms of iterations. So time and epochs are 2 different things. Epochs are the cycles, the forward pass and the backward pass, right? How long it takes to do this is a different story. If you have a very complicated network with so many layers in between, that means one forward and backward pass will take longer than a simple network, right? So we have training time, training epochs, minimum error, size of the network, and size of the network kind of tells you the computational overhead. So take all of this into consideration, compare the networks, and write about it. And then task 5 would be, when you test with the 3-arm planner, you'll notice that the performance is much poor. It's not a good performance. So how can we improve it? What are the best approaches? So that will be a research task. You don't have to implement these suggestions that you find online or you find when you're researching. But what I'm expecting from you, at least the minimum, is to build a network, test it, and critically analyze the results. It is not enough to just do ANFIS for 2 arms and multilayer. If you do only 2 tasks or 3 tasks out of the 5, you will lose marks easily. And I think these are easy marks because the code is there. All you have to do is just edit it. So please look into that. And if you have any questions, let me know. Online, do you have any questions regarding this assignment?
Yes, doctor. Regarding the codes, we can use the same codes in the.
Just a moment, Abdullah, I cannot hear you.